Hello, in this video we're going to look at the projection method to show asymptotic normality. Now this is a pretty darn interesting topic. It's used in non-parametrics to show that the test statistic when the alternative is true approaches normality. This method is used to show that U statistics are asymptotically normal. It's a pretty versatile method. And to keep the video reasonable in length, some of these we're not going to derive, but we'll do it in another video. So the general outline is we have a test statistic such that the expected value is 0. Data comes from some distribution, and V is not a linear combination of independent random variables. So we can't use the central limit theorem to say that V approaches normality. So what we do is we take our test statistic, our random variable, and we project it onto a class of sums of independent random variables. And that projection we're going to call VP. And then we show that VP because it's the sum of independent random variables, we can use the central limit theorem and show it approaches normality. Then we show that our original variable is so close to our projection, and that means the expected squared difference goes to 0. Then we can conclude that V and VP have the same normal distribution. Okay. And our two theorems that we're going to use, and again, not prove this video, we have data, we have some statistic such that expectation 0. Now, if W is the sum of some independent random variable, some function of independent random variables, then we want to minimize this expected squared difference, and it's minimized by this. So the expected value of V given, an X. Then we take the sum of those, and that's our projection. VP is called a projection. V is projected on to the class of sums of independent random variables. And then it could also be shown that this expectation is equal to the difference of the variances. And again, the proof's in another video. And the next big theorem that we're going to use is, if we know that one variable is asymptotically normal and this squared difference goes to 0, then we can conclude that UN has the same distribution as WN. And so we're going to use those two theorems. So now, in this example, we have assume our data follows a normal distribution, some distribution, and here's the sample variance, and here's another formula for the variance, and this is it's a U statistic, so that is kind of nice that we're going to borrow from that. And I dropped my pointer. So I have a video called Interesting Formula for the Variance. You can see that derivation. Now we know its expected value is sigma squared, and so we take s squared minus sigma squared as our variable or test statistic, and expectation is 0. So we're set up for the theorem, the theorem 1. So we find the projection. So we're going to kind of do this in pieces. So ultimately we want the projection of this, but we're going to look at this piece by itself for a second. So the expected value of this given a particular xi, so that means that it's this. So if I is equal to j or k, so if that's I is one of those, then this is what we get, and otherwise we just get this. So, so then this, we expand both of those and we get this. And then if we take the expectation into this, that's a constant because of this. And that's the mean, and that would be sigma squared, or mu squared plus sigma squared. And then this, the expected value is sigma squared. And it better be, because that's what we said that it was. Okay, so now for 4, this is the next step. We're kind of doing it in piecemeal. We're going to take the expected value of V given that. So it's really this, what we have added is the sums, that, and this piece here. And then we get this. So the second part in what we were looking at before goes away. So this piece ends up being 0, so we don't need to write it. And we get this. So now, to find the projection, so we take the sum from 1 to n of each of these that we just found, and we get this. So for whenever there's a little x, we put in an xi, and we take the sum. Well, this can be combined into the squared term, and we have minus x. So this is our projection. So this is in the sum of independent random variables. There's only one xi in each term, and so they're all. And since our data was independent, this test statistic, or this random variable, is a sum of independent random variables. Okay, so now we know that the expected value of our original test statistic is 0, because that's the way we set it up. The variance of it is this, and then the video just before this one, and the title is variance of the sample variance, by Statistics Math, if you want to look it up. And then when we take the mean of our projection, which is this, the expectation can go in here, and then this is the expected value of this is sigma squared, and that's minus sigma squared, so it's 0, so we get 0. And then the variance of our projection. Now, if you go and watch this video, how to derive this is so similar that I'm not going to derive it in this video. So now, because VP is the sum of independent random variables, then by the central limit theorem, we conclude that VP minus its mean is 0, divided by the square root of n, divided by the standard deviation, is asymptotically normal 0, 1. And of course, this is provided that the fourth moment is finite. And then you can substitute this in here, and then leave the n over here, and then take the constants over here, so our limiting distribution of our projection is normal 0, comma mu 4 minus sigma 4. So now we're getting close. So then from theorem 1, we know that this variance, not the variance, this expected squared difference is the difference of the variances. So we plug in the values that we just got, and then the mu's cancel, and then asymptotically this quantity goes to 1. So we have minus sigma the fourth plus sigma the fourth, so it goes to 0. And now from theorem 2, we know that these two quantities have the same asymptotic distribution, and that is that square root of NV is asymptotically normal 0, with a variance of mu 4 minus sigma the fourth. And then we can plug in what we know for V, that's our original, and then we can take that constant to the other side. And so here's the distribution of the sample variance, and it's asymptotically normal with a mean of sigma squared and a variance of mu to the fourth minus sigma to the fourth. Okay, so now hopefully that this made sense. It is a powerful tool that is so used in nonparametrics, again, to show the test statistic in when the alternative is true, because often when the null is true, your test statistic is the sum of independent random variables, and then you can use the central limit theorem or some version of that and show that your test statistic is asymptotically normal. But when the alternative is true, that the independence breaks down, and then you have to project it onto this class of independent random variables, show its limiting distribution is normal, and then show that they're so darn close that it must be normal. And again, this is how U statistics are shown to be asymptotically normal. Well, I hope you enjoyed it. If you did, please like it and subscribe so you don't miss the next one. Thanks. Bye.